talk is from Dr. Thomas Rendall, the host from the University of Bristol. So thank you, Tom, also for hosting this event. It's much appreciated.
Well, we haven't tried lunch yet, but
yeah,
give it a bit.
Totally, I'm starting to have lunch. And Tom's going to talk to us on some recent work on artificial compressibility for SPH using pressure smoothing.
We'll see. I'm just going to, because I'm familiar with the settings. Let's see if we get. There we go. Oh, because they can't see me. Yeah. Okay. There. Right. Okay. Brilliant. I'll just get that. Oops. Keyboard as well. No, that's not going to work. Okay. Right. Yeah. Thank you very much. So this is work that we originally presented at Spheric in Rhodes, and it's so since then we've been working. So going back to obviously the staff involved. So this work primarily Joe, of course, his PhD work. And Joe's been working on a series of different results and extending those since we were presenting at Spheric. So we've got some additional results subsequently. Obviously myself, and then also Brano, Lucian and Jonathan working on the slowed sloshing wing dynamics project. So why are we interested in this kind of thing? So it's a little bit of a roundabout story as to how we came to start working on this this idea. So the sloshing wing dynamics project is trying to model the influence of contained fuel on the dynamic behavior of an aircraft wing. So aircraft wings carry fuel, which is just contained within the outer skin of the wing, known as wet wings. And obviously as the wing flexes, it gets excited primarily in a vertical direction as the wing bends. And this introduces a level of damping to the whole dynamic system. And during aircraft design, that's an important parameter because the level of damping that you can assume has implications for the level of conservatism in the design. So if you have a higher level of damping, or you can prove a higher level of overall damping, you can potentially save weight on other parts of the aircraft structure. So the whole objective of the project really is to try and understand that physical behavior and utilize it to justify an assumed level of damping for analysis by the manufacturer. So this involves quite a lot of impacting fluid behavior as it hits the bottom and top of the tank usually. And you can tackle this with weakly compressible SPH, probably using delta SPH. The delta variation is going to give you an improvement in the spatial smoothness of your pressure. The issue that we had when we were looking at this, and it's probably specifically because it's about impacting fluid behavior, is the residual acoustic behavior that comes from the weakly compressible part of the model. And those acoustic waves keep rattling around, or certainly can do for quite a long period of time. And we wanted to eliminate that sort of behavior. So if you look in the top right, see if we can get a pointer. This is an example of quite noisy forces and integrals of pressure thereby coming from a weakly compressible. That's me standing too close to the microphone, isn't it?
I think it's that.
It's, yeah.
It's the rolling line.
Turn that one off.
I think it's that one. The one.
So I've got this one on, which is still.
Yeah, I think it's the one you take out and now.
Oh, this one. You might be right about that. That's a good point. I think that's turned off. I think that's off. I think it was me leaning over. So, in order to try and address that, we were interested in looking at an incompressible approach. To try and get rid of the acoustic properties that were still there. And so different ways of doing that, of course, you could swap to ISPH, fully incompressible SPH, with some kind of pressure Poisson solve. We were interested in trying to take the sort of the most, or the easiest route into that type of simulation. So we decided to have a look at artificial compressibility as applied to SPH, which has been explored a little bit. And it turned out it's quite successful for the results that we wanted. And it also opened up some similarities between weakly compressible ISPH and the artificial compressibility, which we found quite interesting. Did it work? So yes, it's possible to get rid of the acoustic influences, and that helps with the FSI quite a lot. And these overlaps, I think, are quite interesting. So we'll go through a few of those ideas. So very briefly, a sort of summary of incompressible fluids, which is is a challenge in a short period of time on a single slide, but we'll give it a go. Original work by Chorin looking at the splitting type approaches and similar, well, there are many variants thereof. Starting from momentum equation, take the divergence, that gives us a Laplacian type pressure term. And usually the way this is dealt with in these techniques is to form a pressure perturbation equation. So this divergence and momentum is then formed at different iteration levels. And the idea is to try and solve such that you end up with a zero divergence velocity field satisfying your incompressibility. Now, the prediction of the initial velocity usually comes from some integration of the momentum equation. And generally, this process is followed only once. So you then solve for the pressure using the Laplacian construction that you've got on the right-hand side. And then you advance to the next time step. And you start from initial predicted velocity, and then you come up with a solution for the pressure. And that's the pressure Poisson type approach. It's a little bit unfair to say that that is the approach. There are many, many variants of that. There's a really good paper here by Germond, which goes through all of the different alternatives in quite a lot of detail. One of the interesting things about it, and that is relevant in terms of exploring similarities in these methods, is that you can loop the process, of course, as you would expect. You can continue to iterate at that time step between the pressure and the velocity until they are fully consistent with each other, and that avoids, or eliminates, if you like, the splitting error in this incompressible approach. And there's this paper by Osu where that is explored. So that's the pressure Poisson type approach that is commonly used both in finite volume and also SPH as well. Artificial compressibility is marches a differential system in comparison. So again, linked to Chorin way back in the 60s. So you want your field velocity to be zero divergence, and you can link that to your pressure. So Chorin originally did this in real time for steady problems and marched it in that regard. You can, if you want to do it for unsteady problems, you just call it pseudo time, and it works in the same way within a time step. So using pseudo time, what's happening here really is regions where your divergence condition isn't satisfied. Your pressure is going to increase or decrease until you drive that to a suitable solution. And once that iterative process completes, you've got a zero divergence velocity field, and you've found a pressure field which is consistent with that. So an interesting aspect to this, artificial compressibility has been explored for SPH, but the spatial reconstruction in SPH is quite vulnerable to noise due to its varying nature. Your particles represent your grid, if you like, and so it can give you quite spatially noisy pressure results. So we had to look at this idea. So instead of just driving your pressure with the divergence of velocity, you also use the divergence of the momentum equation. And of course, you're solving that in the limit, so eventually that's going to vanish as well. And this is quite a neat way of, or helpful way of coupling these systems together. And the consequence is that you start to see Laplacian type contributions appearing in terms of pressure, and they do help to suppress noise, which you would otherwise be seeing in your pressure field. And it's driving it to a solution of the momentum equation, which is physically what you want to. So within a time step, you solve that, and then you arrive at your satisfactory pressure field. You can include other derivatives here as well if you want to, so you can go to higher differences. There's potential to adjust the method in various ways. We haven't fully explored all of those. We've had a look at some of them. You could do other things. Now, I said at the beginning that the similarity, and that this is obviously beginning to show perhaps where the overlap between these sorts of techniques exists, in that if you use the splitting approach and you were to loop it iteratively, this becomes really quite close to what you do with artificial compressibility, where you're marching this differential system in pseudo time. Now, Physically, you can also interpret this, so it's perhaps no surprise that this sort of numerical system can be arrived at from physical arguments as well as numerical ones. And that's what's described here in these quite useful papers. So this one by Clausen and later Ramachandran looking at SPH. So you can arrive at a time advancement equation for pressure. And again, you can link that to the physical variables. Obviously, if you were to use this in real time instead of pseudo time, you need to be careful about the constants here. They have a physical interpretation. But if you want to use it iteratively, then you're just solving that and the convergence is satisfied at the end. But you can arrive at this result from physical arguments as well as done in this paper by Klaus. So these techniques really begin, I think, well, at least in my head, they begin to overlap. You can see the similarities there popping up. And the reason it's more obvious is if you include this divergence and momentum here, and then it starts to really line up with what's used in the splitting type approaches. Especially if you consider this modification from OC, where you would do this iteratively in the PPE approach. So quite a lot of similarity. Not surprising because it all comes from the fluid equation, right? So logically, these methods should all fit together. Incompressible mesh-based techniques have often used PPE, of course. Artificial compressibility is a bit less common. Well, if you look for mesh-based approaches, it's pretty rare to see artificial compressibility using those Laplacian terms, but there are some examples of it on the right here by the group that's run by Toutan. So it has been explored. It's probable that they're not as beneficial for mesh-based techniques because the grid tends to help you avoid some of that noise that you tend to see in SPH. At least that's my guess. These papers by Ramachandran have had a look at AC for SPH. And also for understudy ones. So we were interested in this because we thought it could help resolve the acoustic issues that we were seeing. Can it be linked to delta SPH? So this is another really interesting aspect. It'd be nice to tie all these methods together as neatly as we can so that we can understand them on a single page. And if you look at the equations we got, so the physical equation from the time advancement from Clausen, and also the pseudo-time equation for artificial compressibility. And you can start to see that these terms that are popping up, if we look at the bottom result, which is delta SPH, you can start to see that these terms here constructing what essentially become second differences are then fitting in to what is appearing here. So obviously at an exact numerical level, these methods are different due to the way they're implemented and the scalings that are chosen by the different authors, but there's quite a lot of overlap in terms of their origins, I would say. And the only thing that you really need to keep in mind is that obviously with the delta variant, you're looking at density, so it's weakly compressible, and it's written in terms of density, and there's a particular equation of state that you use. But if you were to exchange density and the pressure, these results become importantly comparable, I would say. So there's overlap there, essentially between artificial compressibility and delta. It also means, this is quite useful, that an existing implementation of delta SPH can be converted to be similar to artificial compressibility with some really minor modifications, just including extra loops. It's not a very difficult thing to do. How does it help? So on the left, we've got delta weakly compressible, on the right is artificial compressibility. This is a hydrostatic column and it's supported on an elastic plate. And if we look at you can see from the color flood plot, there's residual acoustic interaction between the elastic plate and the fluid. And this is the displacement. Again, you can see interactions between the plate and the fluid for delta, and the artificial compressibility variants have eliminated that, and that's because the flow is incompressible, so we're not getting that influence anymore. So it does help remove those issues. In terms of cost, so this is worth keeping in mind because we are comparing essentially in our implementation delta SPH, which is explicit, versus what's really an implicit version integration for artificial compressibility. We find that the time step for AC is greater than for delta SPH because that's implemented with an explicit integration here. And there's a trade-off then between the iterations you're doing within a time step versus the increase in the time step size. So this is the cost versus the time as you progress through the simulation. I think the outcome really is that if you're reasonably careful with how you set it up, you can make the cost comparable to delta SPH. I don't think we can really convincingly say it's faster. I don't think it's also slower. I think arguably it's comparable to the existing approach. In some cases it might be quicker, for some slower potentially. This was the rotation case, so there's a little square patch that spins out. If you look at the pressure at the center of the patch, so the lines coming across here, these are the artificial compressibility results, eliminating a lot of the noise features that were seen in the weakly compressible variant. And there's some improvements as well in the conservation properties too. So reasonably favorable results, driven by the fact that you're enforcing incompressibility accurately. Dam break cases. So when we presented this in Rhodes, we didn't have the 3D results yet, but Joe's now worked on those, so we got some 3D dam breaks as well. AC is the two top results and deltas on the bottom. Interestingly, dam breaks in 3D, they don't quite show the same level of noise anyway, arguably because it's a three-dimensional flow, I think. But the reduction in those acoustic signatures are fairly clear. If you watch these animations, you can see that they're occurring in the delta and not in the AC. And that's just because it's a fully incompressible solution. And the pressure field here, again, you can see moving from in 2D from the blue to the red, so eliminated quite a lot of that noise, and again in 3D from the green to the black line here on this curve. So this was something that we felt was important because it helps with the FSI part of it. You don't want to excite your structure with those acoustic waves, and that was important for those sloshing tanks that we were looking at. So this is a dam break case, and mainly looking at cost here. So the comparison really between the green and the black. So in some cases it might be slightly more expensive. For these situations, overall it was as set up for us could be faster in terms of getting to the solution. Obviously, the number of time steps that you take, the number of iterations rather you take, or pseudo time iterations you take for a particular time step varies depending on whatever your convergence criterion is for that time step. So you find that the cost varies depending on the complexity of what's going on in the flow, which is natural. And so when you find collapsing regions of the fluid, it's slightly harder to get the residuals down. The cost goes up a little bit there because of what's going on physically. But as I said, I don't think I'd make any grand claims about it being quicker, but I think that it's, broadly speaking, comparable in terms of cost according to the results that we have here. Sloshing, so this is representing what we were focusing on ourselves. This is a vertically oscillating tank, and here we've got the force that's coming from the fluid, and we're moving away from the blue results, which were contain substantial noise, to the red curve here, which still contains quite a lot of spikes, and that's obviously associated with physical behavior of collapsing void regions and all sorts of slamming type loads in the tank. And then that carries, so the force is quite noisy, that carries through to the acceleration. So once you've integrated that, the inertial effects tend to filter out a lot of the noise in the response, but you still see noise in the acceleration, and it still comes through in the physical displacement results. So the improvement is going from the blue to the red. So we're reasonably satisfied that we've made an improvement in terms of those simulations. What we conclude, weak compressibility For FSI, I mean, for fluid only simulations, it may or may not be an issue, depends what you're looking at. But for FSI, I think some of the noise that you see can be an issue in certain cases, especially that elastic bottom case, which I thought was going to be a really simple problem. And in the end, it turned out to be a little bit more fiddly than we thought, and it sort of led us to this kind of development. So it helps for FSI. It's a really straightforward way to get to an incompressible solution. Doesn't require major modifications. You can fit it into an existing implementation pretty easily. And if you look at it from the point of view of that pseudo-time differential equation, ISBH-AC and delta, if you consider delta swap from density to pressure, they're all quite closely associated. Not exactly, equivalent, of course, but they're very, very similar. And that might mean that there's scope for looking at cross-fertilization between these different methods in various ways. And it could be extended to different forms of smoothing, perhaps, too. So that's it. Thank you very much. I've gone over by a few minutes.
Thank you very much, Tom. Thank you very much. Any questions from the room?
So the flexible bottom still water case. So my first real exposure to it was during a solar program, solar project. And it really struck me that we have lots of people using volume of fluid method in that project, as well as people using SPH. The volume of fluid folks have looked at them and, why do you want to do that? Of course, it's just going to sit there. And the SPH people went, it's pretty difficult. But what happens in counter the so I think the fact that you've managed to get to the point where you've got a solution that for that case is comparable to the VOF solution is from my perspective, this is a huge step forward. Are there any implications in other scenarios for using this where the delta SPH or more sort of typical approach would work? So are there any, apart from things like computational scalability and that sort of thing, are there any areas where this could introduce problems that aren't there if you don't do it? That makes sense.
So we've had plenty of problems during development. I think the problems that we've had, I think they probably were there for the weakly compressible form anyway. I'm not sure that I can think of a situation where using artificial compressibility would cause a problem that didn't exist already. In some cases, that has revealed problems that we were unaware of in the basic formulation for various other reasons. So it's unearthed other things as a result of using it, but it wasn't the cause of them. So no, Jay, what do you reckon?
I would say anything to do with compressibility, you can do with artificial compressibility. That's the one quite biased. But if you have cases where you don't have much acoustic noise, very density perturbations, you might as well use weakly compressible SPH. It's important you don't be fast before other hand.
Yeah. I think that my guess is it's always going to, in terms of cost, it's always going to be within a factor of a couple or a few. Same, very quite comparable. But yeah, if you're only interested in fluid behavior, then you might be fine with weakly compressible. But the thing is, you can incorporate it in the same code, so you can kind of make a decision as you go, really, because it's a relatively minor modification to make. There's an inner iteration to add, and that's it, really. So, and you get the stable time step increases, but of course the cost per time step goes up. But you do get the benefits of the acoustic stuff. So it just hinges on whether or not you want to get rid of that, I think.
So, I use artificial compressibility of other things. And if it's part of the physical model that you do have acoustic waves and you do want to capture them in some form, then that's a better way of approximating them. instead of having a fully compressible set of Navier-Stokes equations. So using artificial compressibility, you capture the acoustic property, the ones that should be there, do remain in the system, while all the noise does get removed.
So yeah, I think you can, we haven't really looked at it, but I mean, if you wanted to use it for a compressible problem, but you could modify it, say, the valid compressible behavior. And there's just a numerical method really to solve that sort of thing. So you could do that as well. Did you do what was that? Finite element or finite volume?
So it was measureless method, but I was using least squares estimation.
One more. Yeah, let's go line first, Paul. Yeah, one line. We come back to the
Okay, so I'll just read it. So the question is, I have to leave. No, sorry, that's the previous one. By pseudo time, do you mean dual time step?
Yeah. So it's I didn't really talk about the integration very much, but yes, it's so the pseudo time or it's dual time effectively. So the AC stuff is in the pseudo time or dual time part, and then the real time integration. I mean, you could. It's important to separate that out. You could do that wherever you wanted, right? The integrator is not linked to artificial compressibility, but we did a second order backward difference, which is fairly consistent with what people use for finite volume methods. But you could use any other integrator if you wanted, of course.
And the follow-on is how do you choose the parameters in the pressure equations when using the AC method?
So there's some flexibility as advantageously as possible is what I would say. So to give you the convergence that you need, I wouldn't say that we've fully got that pinned down. There are certain combinations of parameters that work quite well. Yeah, Joe, this is exactly what you've been doing recently. So you should do it last.
I'm very happy with parameters to be honest. So, in some of the other work people like push compressibility you need to define an effective wave speed of the pseudo time equations. Because in the pseudo time, you're not compressible. You have propagation information like the whole atom speed. And then you can schemes out like weakly compressible solution 10 times the max velocity. Also happy with that because I don't think max for the speed sound, compressibility says it's not really consistent, it's more numerical feature of the pseudo time steps. So our pseudo sound, which is one of its breaking parameters, is just the inverse current condition. We have time step in pseudo time, we know CFL condition for explicitly integrated pseudo time. So we can get a stable wave speed all the time in pseudo time. So we just swapping around the definition of how much of that is in the current condition to always take the pseudo time. What's quite nice as well is the passing terms of the pressure smoothing in our compressibility. At the same parameters as delta SPH, 0.1 times speed times by some wave speed, which is what we find people do for absolute time integration. So actually, I think it's fairly straightforward. It's not really a free parameter that you have to define for the solution. It's defined actually based on that's the ability criteria.
Yeah. I'm aware that time is pressing on slightly. So I mean, we could have your final question if you do. Okay.
I'll be around in a second.
You're gonna get taller.
Okay, so let's thank Tom again, please, for a really nice talk. It's a really clean crash as well, Tom. It's very, very nice.
Yeah.